The rate law of a reaction mathematically relates its rate to the concentration of the reactants and temperature, which are the two factors that affect rate. For a reaction where A and B are reactants, rate law includes only the reactants, and it has the following form. Rate is equal to K, a rate constant, times the concentration of the reactants raised to certain powers x and y. The power x and y is the order of the reaction with respect to each reactant. Those values must be determined experimentally and are not related to the stoichiometric coefficients. Additionally, the sum of x and y is called the overall order of the reaction. Let's discuss what we mean by order. Reaction orders are frequently whole numbers, and in most cases it is 1 or 2, but in some cases they can also be fractional. Additionally, zero and negative orders are also possible. Zero order means the concentration of that reactant has no effect on the rate of that reaction. If you think of it mathematically, a concentration raised to 0 power equals 1. So it takes the concentration term out of the rate law, meaning that the rate is independent of the concentration of that species. The concentration has no effect on the rate of the reaction. A negative order means the reactant slows down the reaction. That's an inverse effect. The higher the concentration, the slower the reaction rate. Order shows by what power a change in concentration affects rate. Let's consider a first order reaction. A is raised to power 1. The reaction is first order with respect to A. If you double the concentration of A, rate also doubles, because twice the concentration of A raised to power 1 results in twice the rate. If you increase the concentration of A by a factor of 3, rate also increases by a factor of 3, because 3 raised to 1, the order, is 3. But if the reaction is second order, A raised to power 2, if you double the concentration of A, twice the A raised to power 2 results in a fourfold increase in rate. Doubling of the concentration results in quadrupling of rate. If you change the concentration by a factor of 3, 3 raised to power 2, the order is 9, rate increases by a factor of 9. What if the reaction is third order? A raised to power 3. If you double the concentration, rate goes up by the third power of 2. The doubling of the concentration raised to power, the order, is 8. Rate increases by a factor of 8. If you triple the concentration of A, 3 times the concentration of A raised to power 3, rate becomes 27 times larger than the original rate. These two graphs may help us understand the effect of order on reactant concentration and rate. For a zero order reaction, concentration decreases linearly at a constant rate, hence the straight line on the second graph. Rate is constant throughout the reaction. Rate is independent of concentration. For a first order reaction, the curving of the line indicates that the rate is decreasing with time. The decrease in concentration causes a decrease in rate. But this decrease is linear, hence the linear relationship between rate and concentration for a first order reaction. The power of the concentration term in the rate law is 1. A second order reaction starts faster than a first order reaction. It also slows down faster. Rate is related to the square of concentration, so a decrease in concentration affects the rate more dramatically. We can also see the nonlinear relationship between rate and concentration. The power of the concentration term is 2. Let's see an example where we can deduce the order of the reaction with respect to its reactants using the given rate law. This reaction is second order with respect to NO and first order with respect to hydrogen. Please note that the orders do not correlate to the stoichiometric coefficients. You cannot determine the order of the reaction using the coefficients of the reactants. This rate law is experimentally determined. So the reaction is second order with respect to NO and first order with respect to hydrogen. And the overall order is 2 plus 1, 3.